we're going to do question 6. The statement reads as follows. A group of grade 12 learners stand outside a fire station when a fire engine races past them on a call. The siren of the fire engine emits a sound of frequency 250 Hz while moving at a speed of 20 meters per second past the learners with flashing red lights. The group of learners notice that the sound of the siren changes as the fire engine moves away from them. Take the speed of the sound in air as 340 meters per second. So 6.1, it says that name the phenomenon described in the underlined sentence above. So the underlined sentence says that the group of learners notice that the sound of the siren changes as the fire engine moves away from them. So definitely we're talking of Doppler effect, right? And then 6.2 says that how would each of the following change as the fire engine moves away from the learners? So let's say, for example, these are the learners. This point here are learners, and this is the fire engine moving in that direction. So it's moving away from the learners. So this is the fire engine. So it's moving away from the learner. So now they say, how would each of the following change as the fire engine moves away from the learners? Write only, greater than, less than, or stays the same. So looking at 6.2.1, the frequency observed by the learners. So if something moves away from you, especially in this case, we're looking at the learners and the fire engine. If the fire engine moves away, what happens is, remember, if you know, velocity is equals to frequency times lambda, right? So meaning if we want to know about frequency, because the question says frequency, we divide by lambda both sides. So you're going to have frequency is equals to velocity over lambda. So the reason why I'm doing this is I want you to look at the learners. The learners are at this point here, right? So the distance between the learners and the fire engine continues to increase, right? The more the fire engine goes in that direction, the longer the distance, right? The more the fire engine goes in that direction, the longer the distance becomes, right? So the distance is actually lambda, right? It's lambda. So the bigger this lambda becomes, the smaller the frequency, right? So means now that you will hear the sound less and less and less the more the fire engine moves away from the learners. The less you hear the sounds because of, you know, waves, sound waves. So the less you hear of the sound. So basically it means now that there's a decrease in frequency. So you can simply write less than, right? So here less than, because it says how would each of the following change the fire engine, or change as the fire engine moves away from the learners. So you can simply write less than, right? So the frequency will decrease as the fire engine moves away from the learners. And then if we look at 6.2.2 says that the speed of sound in air. The speed of sound in air doesn't really change. It stays the same because it really is not affected by the event that is happening, right? So the speed of air is just the speed of air. It's not even the speed of the fire engine. It's just the speed of air. So it's just gonna be the same. So it's just gonna stay the same. Cool. So now we're going to 6.3, right? It says calculate the apparent frequency of sound from the siren observed by the learners. It's really critical that you note this down. It's observed by the learners, right? When the fire engine moves away. So these are critical point. It moves away from the learners at a speed of 20 meters per second. So please check out your formula sheet at the back of your question paper. You'll find formulas of these type of questions under waves, right? We're going to use the formula that looks like this one here. So it's going to be the frequency of the listener being equals to V plus minus V of listener over V plus minus V of S, right, of sound. So multiplied by frequency of sound, right? So we're just gonna, because the it's going to be V, right, velocity of air, which is the 340, and then I'm going to say minus the velocity of the listeners, right, and divide by V plus V of sound, because as the sound moves away, the sound of the fire engine moves away, so it's just going to be positive, and the velocity of listener is this one here, so we're just going to take this sign as negative, right, multiplied by f of s. So it's going to be, we're just going to substitute here, the v of a is going to be 340 minus the velocity of listener, which it's the learners basically, so the learners are stationary, so it's just going to be 0, divide by 340, and then we say plus the velocity of sound, it's moving away, right? So we're just going to say plus 20 meters per second, and then we multiply by the frequency of sound. So the frequency of sound we're given as 250, right? Just look at the statement above. Let me just show you quickly. The statement above, we were given the frequency of sound. Let me remove this. So this is the frequency we're given as 250. So then now you're gonna find your frequency of the listener, right? If you punch your calculator, you should get 236.11 hertz. So this is the frequency of the listener. I'm gonna do 6.4. Says that draw a diagram to show the advancing wave fronts that are produced by the sound as the fire engine moves away from the learner's critical statement. Clearly indicate the learner's position and the direction of the fire engine's velocity in the diagram. So what we know is that we're having the learners here. They are stationary, so these are the learners, right? And then we're having a fire engine here. So this is going to be fire engine. So I'm just going to indicate the direction of this fire engine is moving in that direction. Moving in that direction. So so the diagram of the wavefront is like, so you're just going to indicate, it basically tells us about the lambda and frequency, right? That the further the fire engine moves, then the larger the larger the lambda becomes, right? The larger the spaces between these lines. Let me show you. So it's gonna be like this, right? So this means now that the distance between these wavefronts, so it's gonna be larger towards the learners, but it's going to be smaller at the wavefronts, because the wavefront is the one that is emitting sound, right? So meaning that the distance between these wavefronts, which is lambda, is smaller towards the fire engine, but the distance between these wavefronts towards the learners is larger, right? So that's the whole point of this. So you can make it larger here but smaller towards the fire engine, because it's the one that is emitting sound. So your diagram will basically look like this. So that's how you can draw it, right? So this is your diagram. 6.5, there is a noticeable change in frequency of sound, but no noticeable change in the color of flashing red as the engine move past the learners. Explain this observation. So what I need you to note is this. Let's say I draw my lights. This is the light of the fire engine. It almost looks like the, right, let's just say this is the light. It's on top of the vehicle, right? Yeah, so let's say this is the light. Let me just write lights, and then I'm just gonna write the wavefront, so learners and fire engine, and the wavefront that we drew previously looked like something like this, right? So what this statement is saying, that there is a noticeable change in the frequency of sound. Yes, there's a change in the frequency of sound. Remember that V is equals to F lambda, right? So frequency is equals to V over lambda. So frequency is affected by lambda, right? So this is the lambda. So there's definitely a change in frequency of sound because of this lambda, right? This lambda becomes larger the further the fire engine moves, right? So there is definitely change, but there's no change in this light here that I just drew here. There's definitely no change. I mean, if you look at if you think of an ambulance, right, or a police car, and you see that light that is flashing, right, it's so fast that you can't necessarily see change. You can't see it lighting and maybe turning off, on, off, right? Something like that. It's really difficult for you to notice that. You only see lights that is just flashing, right? So the main reason for that is the following: is because the speed of light, is fast that it's difficult for us to notice, and it's given as 3 times 10 to the power 8 meters per second. So that is the speed of light, if you remember clearly. And then the speed of air, so we're given the speed of air, right, to be 340 meters per second. So as you can see here, the reason why you can't notice is purely because of this reason. You can just base it on this reason, right, and say, okay, fine, the speed of light is larger, right? The speed of light is 3 times 10 to the power 8. The speed of air is 340 meters per second. So basically the speed of light is greater than the speed of air. So the fact that it's greater, which means it's easy to notice the speed of air compared to the speed of light, right? It's easy to notice speed of air compared to speed of light. So that is the reason for this question here.